So in this lecture we will look at flow of blood in a channel or flow of fluid in a channel. As we know that in our cardiovascular system there are number of channels of different diameters. So it is important to understand flow in a channel problem. So in this lecture what we will look at is fully developed flow of a Newtonian fluid and fully developed flow of a Casson fluid, which can represent or which can model the rheological behavior or the viscosity or the viscous behavior of the blood in a channel. So you must have studied in your basic fluid mechanics course that the flow of fluid can be modeled by the conservation equations, and if we want to model the full three-dimensional flow of a fluid, we can represent these conservation equations in the differential form, and these are the conservation of mass and momentum if the fluid properties are dependent on the temperature. Then a energy equation also needs to be solved. But since in our case the flow is isothermal and the fluid is incompressible, that is blood is incompressible, so the properties are independent of temperature. So we just need to solve two conservation equations, conservation of mass and conservation of momentum. So let us look at the general form of these conservation equations first. The mass conservation equation is written in this form. The first term in this equation is rate of increase of mass per unit volume, the first term, and the second term is the mass that is being convected or net rate of mass addition per unit volume by convection. So if you consider a control volume which might be a part of the channel or a channel, so the first part represents, you must see here that these equations are in terms of per unit volume. So that is why it is rate of increase of mass per unit volume, which will be 0 in our case because the density of the blood is a constant. And the second term, it represents the net rate of mass addition that is provided by the convection. So that is flow coming in and the flow going out from the boundaries of the domain. So that is mass conservation equation. And for an incompressible fluid which has a constant density, this equation, this term becomes, for the first term becomes 0. So this equation can be given by divergence of velocity vector is 0. The second conservation that we consider is momentum conservation, and in the momentum conservation, the general momentum conservation equation looks like this. The first term represents the rate of increase of momentum per unit volume. So again this is in terms of per unit volume, rho v is the momentum per unit volume. So rate of increase of momentum per unit volume, first term. The second term is rate of momentum addition by convection per unit volume here. The first term on the right hand side is the rate of momentum addition by molecular transport per unit volume, and the last term is body forces or the gravitational force or any other force. So this can be gravitational force or any other body force. This term includes the molecular transport per unit volume, where P is the thermodynamic pressure, which is normal stress, and T is the tau is the viscous stresses. It can have it will have normal as well as shear stress components. So, for a fully developed pipe flow, let us consider a circular cylinder, a cylinder which has circular cross section, and flow has happening in the axial direction, which we represent as z direction here, and the radial coordinate is r and angular coordinate is theta, and because there is no flow in the angular direction, so that velocity will be 0. So, let us try to understand the assumptions that will be involved in it. The flow is incompressible, so that means the density is constant. It is at steady state, so that means the del by del T term will be 0. Things do not change with time. We do not consider any body forces including gravity in this analysis, and we also neglect the entrance and exit effects, which means the flow is fully developed. So, what fully developed flow means, that with the increase in distance or with distance, the velocity profile do not change. So, if I plot velocity profile at z is equal to z1, and if I plot a velocity profile at z is equal to z2, it remains unchanged. So, what does that essentially means, that jet velocity at z1 and velocity at z2, they are same. So, if we take a first approximation to the gradient, then this will be 0. So, that means del V over del Vz over del Z is equal to 0 for a fully developed flow. Okay, there is no tangential flow, that means there is no flow in the angular direction, and there is no radial flow, as you can see from here, that if there is flow in the radial direction, then the velocity profile in the z direction will not remain same. So, V theta tangential flow is 0, so that means V theta is equal to 0. There is no radial flow, so that means Vr is equal to 0, and the gradients in the theta direction are also 0. So, that means Vz or the z component of velocity or the axial component of velocity is independent of theta. So, V theta is 0 and del by del theta is also 0 for the tangent, the no tangential flow. Okay. So, let us look at the conservation equation again in the expanded form in cylindrical coordinates. So, what we see here is the continuity and three components of momentum equation r, theta and z coordinates, and let us try to see different terms in these equations. Because flow is at a steady state, so all the transient term will go to 0. Vr and V theta are 0, so all the term having Vr and V theta will go to 0. We neglect body forces. Now, the shear stress is a function of velocity gradient. So, if Vz is non-zero, this term gives us that del Vz over del Z is equal to 0. Okay. From here we can see that all the stresses except tau Rz will be 0, because tau Rz have Vz over Vr. All other stresses will be 0 in this case. So tau Rr is 0, tau theta r is 0, tau theta theta is 0, tau r theta is 0, this is 0, this is 0, this is also 0, tau zz is 0 because it will have Vz over del Z. So this we have seen that this is also 0, so this component is also 0, tau theta Z is 0 because del by del theta is 0. So only two components remaining. Again this will be again 0 because tau Z over del Z, and the shear stress will not vary because the flow is fully developed, so shear stress will not vary in the axial direction, so this is also 0. So if we write down the non-zero terms in all the equations, we will end up with this. This we have already said that if the flow is fully developed, then del Vz over del Z is equal to 0. So that means Vz is not a function of Z. So from our two assumptions, that says that Vz is a function of R only, because it was not a function of theta and it is not a function of Z. From these two equations, we see that P is is constant with respect to R. It does not change along the radial coordinate, and P does not change along the theta coordinate. So that again means that P is a function of Pz. So this partial derivative we can change it to tangents a total derivative. You can see here in this equation, this has been rearranged. The second term has been brought towards left hand side, and we see that 1 over r del over del r, r tau Rz is equal to minus dP by dz. So let us try to integrate this, and if you integrate this, what we will end up with, r tau Rz is equal to minus dP by dz dou by dou r of r tau z is minus dP by dz into r. So that means r tau Rz is equal to minus dP by dz into r square by 2, or tau Rz is equal to minus dP by dz r by 2. So this is a general equation, and we get a relationship between the shear stress and pressure gradient and the radius of the channel or radial coordinate. Okay. So this relationship, we can also look at a force balance in a channel. So let us see, if you have a fluid element which has a length of dz and the pressure at the two ends is P and P plus dP, the radius of this fluid element, this cylindrical fluid element, the radius is r, and if this is P plus dP, and if we write the force balance, that pressure will be acting in this direction on the element. So minus dP into pi r square, that is equal to tau into 2 pi r dz So pi cancels out, r cancels out, and tau is equal to minus dp by dz r by 2, and this is an important relationship between the shear stress and the radial coordinate, and this is independent of the constitutive equation of the fluid. It is true for a Newtonian as well as non-Newtonian fluid. So let us look at now for the fully developed flow of a Newtonian fluid, and for a Newtonian fluid the shear stress is proportional to the shear rate, so that tau is equal to minus mu del Vz by Vr. So if we substitute this here, we will end up with minus mu del Vz by del R is equal to minus dp by dz into r by 2, and if we bring mu on the other side, then it will be 1 over mu dp by dz r by 2. So let us integrate it, and we will get Vz is equal to 1 over mu dp by dz r square by 4 plus c, where c is a constant. So this has already been integrated for us. So we end up with this equation for Vz. So having obtained the velocity profile in a fully developed pipe flow for a Newtonian fluid, let us now, we can also derive the flow rate in the channel. So flow rate, using this profile, we can say the volumetric flow rate, which is Q is equal to integral 0 to r V z into 2 pi r, which is the area of a differential element that we will take on a cross section into dr. Okay. So after the integration, we will obtain this relationship between flow rate and the pressure gradient. This relationship is known as Hagen-Poiseuille law, which says that for constant pressure gradient, Q is proportional to r to the power 4 for given pressure gradient. For given dp by dz, Q is proportional to r to the power 4, or for given Q, delta P is proportional to, or delta P by L for that matter is proportional to r to the power 4, because r is because L for a channel, if it is a constant, then we can say the pressure drop is proportional to r to the power 4 for given flow rate. Now this has very interesting implications in blood flow. We can show using this relationship that delta Q over Q is proportional to 4 delta R over R. That means a very small change, only 1% change in flow rate will cause 4% change, 1% change in the radius will cause 4% change in the flow rate. Similarly, if the flow rate is constant, then very small change in the radius will cause significant change in the pressure drop. So, this is for given pressure drop, whereas this is for given or for constant flow rate. So, this is an effective way in the cardiovascular system to change the blood pressure. So, the hypertension is generally caused by narrowing of the blood vessels become narrow and the pressure increases significantly. Similarly, the muscle tension or the pressure hypertension can be reduced by smoothing the muscles. Okay. So, Hagen-Paiseli flow has a number of interesting implications in the cardiovascular system. Now, having looked at the flow in a flow of a Newtonian fluid in a circular channel, now let us consider the case of a non-Newtonian fluid. So, we will consider the flow of a Casson fluid. Now, why Casson fluid? Because the first and foremost reason is because blood is a non-Newtonian fluid which follows the Casson model, or which has shown that Casson model can be used to model the flow of blood accurately. Okay. Another reason is because, as you can see in this relationship, Casson model includes a yield stress behavior as well as a power law kind of behavior. So, by understanding how we can model flow of a Casson fluid, we can also use the analysis or some parts of the analysis to model of the fluid which show yield stress behavior, for example, Bingham plastic fluid, or we can model the flow of a power law fluid using the similar methodology as we will use for Casson fluid. So, the fluid shows a yield stress, and as we have seen in the previous slide that for all the fluids, tau is equal to pressure gradient into R by 2. That means tau is proportional to the shear stress. So, if I plot this on a xy graph, let us say on the y axis I show radius as shown in this figure and tau. So, from this relationship, tau will be 0 at the center and then it will increase and become maximum at the wall. So, let us call this value as tau wall. Okay. Now, yield stress means that below yield stress there will be no flow, or the shear rate will be 0 if there is no flow. So, because as we can see from this plot that the shear stress is maximum at the wall. So, if the value of the yield stress is more than the wall shear stress, then there will be no flow in the channel even if some shear stress less than the yield stress is being applied. So now, if the yield stress is more than stress on the wall, so let us draw this plot again, where we plotted yield the stress versus R curve. If tau y, which is yield stress, is less than tau wall, then it will fall somewhere in between. Let us say that at tau is equal to tau y at this point, where the shear stress is tau y, let us say the radius we call it RC, or the core radius. Why do we call it core? We will be looking at it in a minute. If the radius, that means that below RC, or when the radius is less than RC, in that region the stress is less than, so we can have two regions, this is core, and in this region tau is less than tau y, whereas in this region tau is greater than tau y. So when the tau is greater than tau y, that means when the radius is between RC and R, then fluid will follow root tau is equal to root tau y plus root m gamma dot, where gamma dot is the shear rate. Now, if the radius is less than R, then the shear rate will be 0. However, that does not mean that there will be no flow at the wall. So let us draw this picture of the channel again, and this is RC. So we will have a velocity profile something like this in the region where R is greater than RC. Now at this point, at the interface, or at R is equal to RC, from this equation we will be able to find out what is the velocity, and the velocity in this region, in the core region, will be the same. So the fluid will have two kind of regions. One is the core region, where the fluid move like a rigid body, move like a plug or a piston, and there will be gradients in the near wall annular region. So we can analyze the flow field for a Casson fluid by considering these two regions separately. A similar approach is required while considering the flow of any non-Newtonian fluid which shows the yield stress behavior, for example a Bingham plastic fluid or a Herschel-Berkeley fluid. Okay. So let us consider the region where R is greater than RC. It will follow this law. So if we rearrange this, we will obtain this relationship. Let us work out the step in between. So we will have root m gamma dot is equal to root of tau minus root of tau y, and if we square on both the sides, then we will get m gamma dot is equal to tau plus tau y minus 2 root tau y. Okay. So we have obtained a relationship between the shear rate and the shear stress. We have shear stress in two terms on the right hand side, and one is the shear stress only, and the other term has root of tau there. Okay. So now, because our objective is to find out the velocity profile, so we will substitute the shear stress as a function of radius, which also include dp by dz. In for all these cases, dp by dz is a constant. So the pressure is we are varying linearly, or the pressure gradient is a constant. So if we substitute these here, what we obtain is this. We can substitute that shear rate is equal to minus del Vz over del R is equal to 1 over m, as it is. In place of tau, we substitute minus dp by dz R by 2 plus tau y. We will not touch it as of now. 2, again we substitute the value of shear stress as minus dp by dz R by 2. So let us now integrate this equation, because the right hand side have only R or constants, because yield stress and the pressure gradient both are constant and independent of the radius. So we can integrate this to obtain Vz is equal to minus 1 over m within bracket minus dp by dz R square by 4 plus tau y R minus 2 root of tau y minus dp by dz. Now 1 over root 2 R to the power 3 by 2 divided by 3 by 2. So if we write this down, this is what we get, and an integration constant. Now we apply a no slip boundary condition on the wall, so that we can find out this integration constant c. So we can substitute and get the velocity profile. So we can write that Vz at R is equal to capital R is equal to 0 because of the no slip boundary condition, and we substitute R is equal to capital R in the equation. So minus dp by dz capital R square by 4 plus tau y capital R minus root of 2 tau y minus dp by dz capital R to the power 3 by 2 plus integral constant. So if we say this equation as A and this equation as B, what we can do to eliminate C is A minus B. If we do that, Vz minus 0 is Vz minus 1 over m, and now we can subtract the terms one by one. So minus dp by dz multiplied by R square minus capital R square by 4 plus tau y R minus capital R minus this all root 2 tau y minus dp by dz R power 3 by 2. What we have missed here is this is divided by 3 by 2 here. So this will be 2 by 3 and this all inside. Now if we look at this further, this equation, so Vz is equal to the same equation, and Now we can substitute this in terms of RC. Tau y is minus dp by dz RC by 2. So if we substitute and obtain this in terms of RC, the radius of the core, so we will get velocity profile Vz is equal to minus 1 over m minus dp by dz, and this will be r square minus capital R square by 4 plus minus dp by dz into RC by 2 multiplied by R minus capital R minus 2 by 3 root 2 minus dp by dz. We have 2 dp by dz, so squared into RC by 2 here, and this is multiplied by R power 3 by 2 minus capital R power 3 by 2. So if we take 1 by 4 minus dp by dz out from this bracket, minus 1 by 4m minus dp by dz, what we are left with is minus R square minus capital R square here, and this will be, because this is 4, so we can multiply by 2 and 2 here, so that will be 2 RC R minus capital R, and again if we multiply this by this 2 will cancel out anyway, multiplied this by 4 by 4, so we have 8 by 3, and this 4 will go out, and dp by dz has gone out already. What we are left inside the bracket is root RC R to the power 3 by 2 minus capital R by 3 by 2. So that is a velocity profile in terms of the m constant, dp by dz, and RC and R. So having obtained this velocity profile, now remember that the velocities that we obtained is a general velocity profile, and this is only in the annular region. So if we want to obtain, or if you want to obtain a flow rate, we need to obtain the velocity in the entire region. So at this point where R is equal to RC, by continuity of velocity we can obtain the velocity of the solid core if we substitute in the velocity profile obtain R is equal to RC. That was the primary reason why we were interested to substitute tau y in terms of RC, because we will know tau y anyway, but we have substituted this in terms of RC, so that this equation we can also find out, from this equation we can also find out the velocity of the core. So after substituting R is equal to RC, small r is equal to RC, that is the velocity profile. Okay. Now to obtain flow rate we need to integrate it 0 to r Vz 2 pi r dr, and because the velocity profile is different in the core region and in the annular region, so we can divide into two parts. First we can integrate 0 to RC Vz c 2 pi r dr, and then we can integrate RC to R, this is Vz 2 pi r dr. So after substitution we will get after the integration and the substitution we will get this flow rate, which is pi r to the power 4 by 8 m minus dp by dz into this entire factor, where this factor, the psi in this factor is equal to 2 tau y by r divided by minus dp by dz, this you might notice this is yield stress, and this is the pressure gradient. Okay. So, in this lecture what we have looked at is fully developed flow in a channel for the laminar flow of a Newtonian fluid and of a Casson fluid. In the Casson fluid, there are two things that we should remember, that if there is an yield stress, then we need to think about that the fluid in the channel will have two regions. In one region where the shear rate will be varying across the cross section, whereas in the center the fluid will flow as a core. Now, another lesson for power law fluid says that we can rearrange the equation as gamma dot is equal to shear rate to the power alpha, where alpha can be any number. And once we have rearranged this, what we need to know is we can substitute tau is equal to minus dp by dz r by 2, and when we substitute this for constant pressure gradient, we can get the velocity gradient in terms of radius, and then we integrate it to obtain the velocity itself. Okay. And now our task is to find this constant in the integration, and this can be found by the use of a boundary condition, the no slip boundary condition at the channel wall, which essentially say that when a liquid is in contact with a solid wall, then there is no slip between the fluid molecule that is in contact with the wall and the wall. So, V fluid at the wall is equal to V wall. Whatever the velocity of the solid wall will be the velocity of the fluid that is in contact with the wall, and in this case, because the pipe is stationary, so this is 0. So, we will use this boundary condition that at r is equal to capital R, where r is the channel radius, the velocity Vz is 0. So, if we substitute that, then we will end up with Vz is equal to 0 at 1 over mu dp by dz capital R square by 4 plus c, and if we subtract, then we will get 1 over mu minus dp by dz capital R square minus small r square. So, you might notice that if you substitute from this equation, let us say this is equation 1 and equation 2, and if you subtract 2 minus 1, you will get this. Okay. So, what we have done here, we have obtained the velocity profile for the Newtonian fluid in a channel. Now, if I want to obtain this in terms of V maximum, then I can say that at Vz at r is equal to 0, that will be V maximum, right. So, V maximum is equal to 1 over 4 mu minus dp by dz. So, we can write Vz is equal to V max into capital R square minus small, this is R square. So, if we divide V by V max, then we will get this is equal to divided by R squared, or Vz is equal to, so what we will get, Vz is equal to V max into 1 minus small r square by capital R square. Okay. So, this is a parabolic velocity profile in a channel, which is also known as Hagen-Paisele flow. You can also calculate the flow rate and average velocity for this pipe flow. Now, we will look at the flow of a Casson fluid. For a Casson fluid, you might remember from the previous lecture that the constitutive equation, that is the relationship between shear stress and strain rate, is given by this formula, that is the square root of shear stress is equal to square root of yield stress plus square root of m gamma dot, where gamma dot is shear rate and m is a consistency index. So, again for this fluid also, the relationship between tau and r is still valid, and this shows that tau is proportional to r by 2. For this fluid or Casson fluid shows a yield stress behavior, that means if the applied stress tau is less than tau y, that means flow is, there is no gradient, right. So, from this what we can see or what we can observe, that tau in a channel will be maximum at the wall at r is equal to capital R. So if shear stress at the wall is less than the yield stress, that means there is no flow in channel. However, if shear stress is greater than the yield stress, then it will follow Casson fluid formula, or it will follow the Casson fluid model. So from this equation it is clear that the shear stress will in a channel, the shear stress will be 0 at the center and it will vary to a value tau w here. Now somewhere in between this will be equal to tau y. Let us say this radius as RC. So that means that in the channel the condition will be such that there is yield stress, the stress is less than yield stress in the center, so there will be no gradients or zero gradients there, whereas near the wall above RC there will be gradients. So the this core region will flow as a rigid body and the gradients will be present in the annular kind of region there. So for RC is rigid body like movement will be in the core and the Casson equation will be valid in this region. Okay, let us now look at this equation. So again write down this Casson equation and let us rearrange this. So if we want to write down m gamma dot, this will be equal to root of tau minus root of tau y squared. That means m gamma dot is equal to tau plus tau y minus 2 root tau y. Okay, now we substitute tau is equal to minus dp by dz r by 2 in this, and what we will end up with this equation, that shear rate minus dvz by dvr, which is equal to 1 over m. Tau is replaced by this value minus dp by dz r by 2 plus tau y, which is yield stress, minus 2 root of tau y into, again we have substituted tau here. Okay. Further, let us move on to this equation and we integrate and get the velocity from this. So if we take minus sign on the right hand side, it becomes Vz is equal to minus 1 over m. The first term minus dp by dz r square by 4. The second term tau y is a constant, so tau y r minus 2 root of tau y minus dp by dz is a constant. 2 by 2 has become a root 2 here, and there is r, so this is r to the power 3 by 2, so that will be divided by 3 by 2. Okay. So now we apply, there is again an integration constant here. So now we apply no slip boundary condition at the wall, and we can eliminate C. So if we do that, then we will end up with Vz is equal to minus 1 over m minus dp by dz r square. So in this place now we are writing it for the wall. So capital R square by 4 plus tau y capital R minus 2 root 2 by 3 root of tau y minus dp by dz r to the power 3 by 2 plus c, and we subtract equation 2 from equation 1. So this will be 0 at r is equal to capital R. So we get from 1 minus 2 Vz is equal to minus 1 over m minus dp by dz r square minus capital R square by 4 tau y r minus capital R, and this term, sorry for this mistake, so 2 root 2 by 3 tau y minus dp by dz r to the power 3 by 2 minus capital R to the power 3 by 2. And now bring this here again, and in this let us notice that tau is proportional to, or tau is equal to minus dp by dz at r by 2, and if we do that at r is equal to rc, where tau is equal to tau y. So we substitute this in this equation, then we get this value that tau y is equal to minus dp by dz rc by 2, and we get this velocity profile. So after substituting, we will get Vz is equal to minus 1 over m, we can take minus dp by dz out of this bracket, four also can be taken out. So this will be small r square minus capital R square plus tau y we replace by minus dp by dz. So minus dp by dz has gone out, there is a 2 there, and we have taken 4 out, so we will multiply by 2 here, 2 rc small r minus capital R minus tau y is equal to minus dp by dz. So minus dp by dz has gone out, and within bracket what remains is rc, 2 and 2 is cancel out, so